To take a look at the idea of the spread of points around the mean, I want to look at the concept of variance, and we're going to use this thing I call this the crazy dart game. But you have to imagine that what I've laid out here on the board is actually a dartboard that's a flat 2D dartboard, right? So that or 1D, I guess it is, just along this line. And we're going to have two different participants today. Fisher is one of them. It happens to be that we have a couple of dogs, Fisher and Finna, and I am going to give them the honors of playing darts today. Fisher and Finna will be shooting their darts at a target here, and so their target is clearly going to be the 7 in the middle. And I've gone ahead and chosen some darts for them to throw. And what I want you to think about is measuring how good a dart player they are. And the first one, Fisher's going to throw his first dart, and I'm going to make Fisher's darts be these blue ones here. Fisher's going to land right here at the 7. And then his next toss is going to be way down here at the 0. His next one is way up here at the 14. His next one is way down here at the 0. And his next one's up here at the 14. And so that's Fisher's score. And I'm going to write his score down here like this. 7, 0, 0, 14, 14. And Finna is going to play, and she needs a different colored dart. So let's give her, she's going to go with fuchsia. And then her score, her first dart is going to be thrown here. It lands at about the 7 area. But her next dart is off, and it's at the 8. And her next dart is at a 6. And her next dart's an 8. And her next dart is a 6. Now, you can clearly see that we know that the dart player here, Finna, has made a much smaller collection of points. And Fisher's collection of points is really a lot larger, right? It's spread all over this area. But we need a quantitative way to measure this. And so if you're going to measure this to determine the winner of the accuracy, let's go ahead and write down Finna's score as being 7, 8, 8, 6, 6. If we consider different ways of doing this, you could use the range. And Fisher would have a range of 7, right? So his range would be 14 minus 7. 14 minus 0 equals 14. So he would have a big range. And Finna would have a range of 8 minus 6 equals 2, which is quite a small range. So that would work okay, but it doesn't give us a whole lot of information about how the points are spread around the middle. We could also go in and look at our dart game and say, well, let's consider the deviations. And when I say deviations, I mean, in Fisher's case, let's go from his central value. Let's calculate the mean for each of them to find their central value. Okay, so the mean is going to be written here. I could write it as the sum of x sub I equals 1 to n over n, right? If you wanted to get equals x bar. And the mean then, x bar, is going to be equal to, and I quickly did this with my calculator to add these numbers up. 14 and 14 is 28. 28 plus 7 is 35. 35 divided by 7 is equal to, by 7, 5. 35 divided by 5, which is the number of observations, is equal to 7. And that's the mean. And if we look at Finna's and do the same math, we will find that x bar equals, let's see, 6 and 6 is 12, 8 and 8 is 16, so 12 and 16 is 28, and plus 7 is also 35 divided by 5 equals 7 as well. So the means are the same in each case. So that doesn't give us a lot of information about the spread of points, though, about those means. So one way you might intuitively imagine doing this is just looking at the total deviations. So you could say things like, all right, let's go to Fisher's score and say, he's got these huge deviations like this and like this, right? And really big ones here. And you could add these deviations up. And you could compare those to Finna's deviations, which are really short like that. You could draw these like little sticks that represent how far each of her points are from her central value. And so Finna's sticks would be, we could do that, but what would happen? Let's go down and take a look at what happens. We do that for Fisher's. We would subtract the mean from each point to find the deviation. So if we did that, subtract the deviation, subtract the point, right, equals what we call the I'm going to write DEV right here. So we have a 0 deviation for the first one. We subtract 7 from all of them, right? Like that. That's the mean value. And so this makes -7, this makes -7, this makes 7, and this makes 7. And if you were to add up the sum total of those would all equal 0. Oh, geez. So the deviations all added together equal 0. That's not really going to be very helpful for us. So I can show you the same thing happens here on Finna's side. 7 minus 7 equals 0. We subtract the mean from all of them. And what we get here is 0, and then we get 8 minus 7 is 1, 8 minus 7 is 1, 6 minus 7 is -1, -1. Again, they all add up to 0. So as a result, that's not good. So I'm going to circle this and say this is not very helpful, all right? Not helpful. I think that's kind of funny. This is just not a helpful solution. I think it's worth thinking about because it is intuitive. It's an easy way to think about how to do this. How can we fix the problem that they all add up to 0? We try to get rid of the signs, and you can't just sort of go around getting rid of signs like changing all the negatives to positives. That doesn't really work out well in the long run. But one thing we can do is we can square those deviations. And because a squared number is always positive, I'm going to go over to Fisher's column and write deviations squared, because I still like the concept of our deviation. So that's going to be 0 squared, and this is -7 squared. But watch, when I square -7, it's going to be 49, right? It's a positive number. -7 squared is going to be 49 again. +7 squared is also 49. And the other 7 there. Now these numbers are starting looking like some positive numbers. 0 times 0 is 0. And I'm going to take out my calculator really quick and figure out that 49 times 4 equals 196. So I can take 196 is the deviation squared, right? And I can do the same. So that's a measure of how far Fisher was from the target. Let's do the same for Finna. 7 minus 7 is going to be 0 squared. That's pretty easy. 8 minus 7 is 1 squared, 1 squared, -1 squared, and -1 squared. 1 squared is 1. 1 squared equals 1. -1 squared equals 1 equals 1. The total there is 4. Quite a bit easier math. So that's his deviation squared. Or hers. Sorry, Finna's. Yeah. So we now have two different measures there. Remember what our points look like. These purple ones here are the Finna scores. And the blue ones down here are the Fisher scores. And so his are really, widespread in there. Now we have a good measure. I'm so happy with that measure. I'm going to circle it on here. Maybe I'll even highlight it, right? This is a really cool measure, the deviation squared. The deviation squared will actually increase with the number of observations, which means the more darts you throw, you're always going to increase your deviation squared. So it's not a great score if the sample size isn't the same. So what we can do is take the average of the deviation squared. So what I'm going to do is take those deviations squared and divide by the number of observations, which is 5 in this case, and it's 5 in this case. So this one is going to be 4/5, which is 0.8 for Finna, and it's a little trickier for Fisher. I have to get out my calculator, but I can just divide by 5 equals 39.2. Now we still have a very good measure there, and I'm going to highlight that measure, 39.2 and 0.8, to compare these two. Now notice the measure that we calculated there is easy to think of on your own because you just take how far you are from your central value, being your mean, and you square that number, and then you add them all up, and then like we did here with in Fisher's column, we add them all up, and then we take their average. And so that number is really the average squared deviation from the mean. ASDM is how I like to remember that. So you'll never need to memorize the formula again. And this is called the variance. This is actually the statistical term, the variance, which is recognized as sigma squared. And if you take the square root of that, you can get the standard deviation, which is equal to this. Now they have the same information in these two. One is simply the square of the other. That's like telling you I have a number here, it's 2 squared, and the other number is just 2, right? So same information in those two. And this is how I like to think about the calculation of the variance.